So something that we did, and this is why like I made up a new example because I couldn't remember the old example. We had an improper integral. It was of a rational function where we eventually ended up with some natural logs as far as our antiderivative goes. We plugged in values. We have two different limits, one on the left, one on the right. And in our process of evaluating that limit, we got to this, or an analogous point of this step, where we went, well, I mean, if I'm taking the limit from the left for b, so I'm coming in through the negatives, but I have this absolute value involved, I can switch this to a limit from the positives and get rid of the natural, or get rid of the absolute values. The absolute values take negatives and return them to positives. And then now we got the same limit here, and then we can subtract the limits and we get 0 for that final answer. And this is a perfectly good example of something called the Cauchy principal value. The technical definition of convergence for these vertical asymptote improper integrals where you need to split it up to a left and a right side, you're integrating on both sides of the vertical asymptote. The definition requires that they both have to converge in their own way. If either one diverges, the whole thing is considered divergent. And that was my mistake.
I see.
So, because this one is going to diverge in its own right, because we got a limit going to 0 of the natural log, and that's going to negative infinity, and the same thing here. They do technically diverge according to the definition. As soon as one diverges, the whole thing diverges, and it's over. Even if technically at the limit evaluation step, this is an infinity minus infinity, and it is therefore an indeterminate form. The definition for convergence for these vertical asymptote improper integrals requires that they both converge from both sides for the thing to be even considered convergent. No indeterminate form shenanigans. Cauchy's principal value is a way of ascribing a real number value to divergent stuff. There is this sort of meme math result of you take 1 and you add it to 2, and you add it to 3, and you add it to 4, and then you add it to 5, and then you keep adding bigger and bigger and bigger numbers up to infinity, and you get negative 112. Solomon, you're right, I assume you've seen this before.
Yeah, isn't that something to do with that? Either the zeta or the eta function?
The Riemann zeta function, yeah. And that is an example of Cauchy principal value. In no way do you add up infinitely many positive things. Do you end up with a negative thing? Let alone a negative kind of small thing. So that's an example of the Cauchy principal value. It is something so very clearly divergent that we can still ascribe a real number of value to it. And the usefulness of that value sort of depends on what on earth we're going to do with it. In the case of the Riemann zeta function, it would be the analytic continuation of the Riemann zeta function.
That's 1 over x dx.
Yes.
Okay.
So, moral of the story, I'm sorry, I made a mistake.
Wait, where you make a mistake at?
Here.
Because in the notes, this says you said divergent.
Did I say that?
Yeah, you said it diverges. That's what I got in my notes.
For the example that was...
1 over x dx. You just
Oh,
said
no,
it goes
not
to
that
infinity.
Also, the limits are totally different.
Oh.
I was talking about this one. We got a vertical asymptote here, and we're integrating on both sides. And we get a number down here.
Okay.
Yeah, what's up?
Okay, big purr. The king be knowing.
Our
The
time
king
is
be
not
knowing.
gonna decide if they go off to infinity
Don't play with the
or
king.
diversion, because those two links are.
Just like that, exactly.
So
Exactly. He the king, I'm the queen.
What you're saying, you messed up from.
He won't be so bad.
If we have a vertical asymptote and both sides are divergent going off to infinity, you cannot say that limit is convergent anywhere because you have divergent species, I guess.
Yeah,
He's
even,
steady
even
tips.
if it is an indeterminate form and you L'Hopital's rule that indeterminate form and get a actual result, it's still divergent, or it's still considered divergent.
So the thing with that though, when we had that integral on there, I feel like we didn't even have to L'Hopital's rule it because there was some algebra you could have done earlier to just get a.
So like the problem isn't necessarily the use of the L'Hopital's rule.
Okay.
The problem is that we took these two different integrals, we found their antiderivatives,
Yep.
we plugged in a whole bunch of stuff, and then we found that those limits canceled out, either algebraically or through L'Hopital's or whatever, right? We combined the two different divergent parts of these different integrals, and we found out that they kind of diverged in precisely opposite ways and kind of canceled each other out. That was the mistake.
So, okay.
You
Like,
can't
we can't-
combine the divergence
Yeah.
of these different
We can't like know those infinities are the same kind of thing.
Yeah, once you get one to diverge, the whole thing is divergent. Right, and that's part of the definition of convergence for these vertical asymptotes. If you look in Stewart and you see like the little red box for these kinds of improper integrals for vertical asymptotes, at like the very bottom, there's like a one-line sentence that says, and they both need to converge in their own way.
I see.
Focus.
But.
They ain't talking about
another
nothing.
question. We were talking at the end of class Wednesday about like wave functions that bound off to infinity but they cancel out each other. Would that help at all with these or just?
Nope.
Nope. Got you.
No, totally different thing. Right? This is only for the case where you're dealing with the improper integral of a vertical asymptote, and you're integrating over that vertical asymptote. If you had an infinite in one of the limits, everything we did was perfectly fine. It was just one particular case where we combined the different divergent parts of different integrals and we found the difference.
If they're the same integral, it would be fine, but because it's
Yeah.
separate right now.
As soon as we need to split up this integral because we had that vertical asymptote at 0, we can kind of focus on these one at a time. The second either one of these diverges is the second the whole thing diverges.
So when it's both converge, we can then
Yep.
combine the back?
Yep.
Okay, gotcha.
If they both converge, we're good. If either one diverges, the whole thing diverges. And if they both diverges, the question is, why did he find it that the other one diverged? And clearly just stopped that being on the first one diverged. So that was my mistake. I shouldn't have taught you guys about the Cauchy principle value. That was my fault.
But now we know.
Yeah, now you know. I always find that there's like sort of interesting wisdom in these things. You know, if the mistake hadn't been made, we never would have talked about the Cauchy principle value. And Solomon would never have been able to talk about the Newman zeta function. Right? Wasted opportunities, right, Solomon?
Yeah.
So that was my fault. I am sorry. I will try not to make a mistake like that again. I am human. I will probably make a mistake like that again. Sorry.
So the answer is divergent.
The answer is divergent.
Okay.
It's not negative natural log 2. The Cauchy principal value for this integral is the negative natural log 2. That is because it is the recoverable real value solution part of a divergent integral. It's divergent.
Sounds good.
Alright. With that out of the way, let's talk about something that like I'm not super like an expert in. Mainly because like I've never really found much use to this. Numerical integration. This is going to be a relatively short section, and it's going to have a relatively disappointing conclusion, at least from like the interest perspective of it. When we're talking about numerical integration, we are talking about methods for which we can get approximate values. So if I have an integral of a function from like a to b of f of x dx, if I know the antiderivative or I can find the antiderivative of f of x, then you find the antiderivative and you use fundamental calculus on this. Use antiderivative and fundamental theorem of calculus to get an exact answer. But this is kind of a big assumption. This is a big assumption for me. So I assume it's kind of a big assumption for students as well. Given just a generic, random smattering of function notation and symbols inside of a function, the probability of being able to find an actual antiderivative goes down dramatically. Right? We have very specialized tools for finding antiderivatives. They don't always work. Finding antiderivatives is a genuinely difficult task. So this is where numerical integration comes in. What if, in sort of the like maybe nicest case for the problem, what if we can't figure out an antiderivative? Or in the worst case for the problem, there is no antiderivative. Of which there are certain functions where it is surprisingly easy to find functions with no antiderivative, and by this I mean a closed form antiderivative. One of those being antiderivative of e to the negative x squared dx. Right, this is sort of a classic integral. This does not have a closed form antiderivative. It's also considered a classic because if we were to graph this, it looks like a bell curve. Because it is a bell curve. It is called Gaussian, or a Gaussian. And so when it comes to this sort of idea of closed form antiderivatives, what we're really talking about is there a finite sum of elementary functions, so sine, cosine, e to the x, natural log of x, power functions, sort of familiar functions that you've been working with all this time. Is there a finite sum of those that can serve as an antiderivative of this? And the answer is no. We cannot take a finite sum of those kinds of functions and make an antiderivative for this. Which means this thing does not have an antiderivative for practical purposes. this has an antiderivative, and it's kind of easy to find with U substitution.
Oh, right.
This does not. That X in the front makes all the difference. So that's sort of the question numerical integration is trying to ask. If we can't figure out an antiderivative, or if there is no antiderivative, what do we do? And the answer is, at least at the beginning, stuff we kind of already know how to do. Midpoint rule. If we got a function, and we're integrating that function from A to B, and we don't know what the antiderivative of this function is, what we can do is do some midpoint rule. Pretend like these are evenly spaced rectangles, please. Right, so method 1. Midpoint rule. Right, we sort of determine how many intervals we want for a desired result. So, how many subintervals is wanted? And that's going to tell us the amount of precision that we're going to get in our approximation.
Are we still gonna take the limit, or are we gonna get an actual real value?
Nope, for the limit. We're looking for an approximation. If we took the limit, this would be an exact value. However, involving that thing to the actual evaluation of that limit is actually analogous to finding an antiderivative. Which we have just kind of, tried to establish. We can't do that. Right? For whatever reason, it is not something that is feasible to do. Maybe it's just a really, really hard antiderivative. Maybe there is no such antiderivative. So the evaluation of that limit can't quite be done. So number of subintervals tells us the precision for the approximate value. And we're going to be okay with taking an approximate value. We only needed 7 digits of pi to make it to the limit. That's how many digits of pi mass it is for the Apollo program. So we're going to be totally okay with an approximate value here. There are certain advantages to midpoint rule from a computational side of midpoint rule. It's relatively easy to code and program, right? Say you want 7 intervals, well, take the length of B to A, divide by 7, get the midpoints of those, so take the average of those 2 endpoints of each of the subintervals, plug them in, add them up, and you're kind of done pretty quickly from a computational point of view, from a coding point of view. There are a few things that we do kind of want to consider when it comes to approximate methods. We have the rate of convergence. Which is a fancy way of stating, well, how quickly does this approximate value approach the true value? And there are a couple of different ways that, theoretical computer scientists and math people kind of judge particular algorithms for getting this sort of precision, for getting the rate of convergence. And the usual methods kind of involve, let's just use this algorithm to calculate pi. something we already know to a couple billion digits of precision, and we'll just see how far along the rate of convergence goes, and compare whatever algorithm wins. So as far as the rate of convergence goes for midpoint rule, it's actually kind of not bad. It converges on the order of a cubic, if I remember right. So it's actually kind of converging relatively fast compared to this. And then the other thing that we're kind of concerned about with these numerical methods, with these algorithmic methods, we are concerned about the number of operations we're using. Right, Solomon, I think you said you were going into computer stuff.
Yeah.
Big O notation. We're really concerned about the number of operations we use and we expend for these particular algorithms. If we have an algorithm that has a really, really, really fast rate of convergence, but it needs like 15 billion operations per step, it's not really that good of an algorithm because we're going to need a ton of RAM to actually run that thing. And the number of operations here is kind of small.
Should I get my nails done?
I believe the big O here is just a vex, or just a ben, right? It's a linear big O, which is not bad, right, Solomon?
Yeah.
You're the expert on big O, right? Because you're the only other student who knows about big O notation. So linear big O, I think. Zach, do you know about big O?
I have no clue.
Big O, O for operations. It's a function that measures the number of operations used in an algorithm.
Not exponential.
Exponential's really bad, right, Solomon?
Yeah.
If you have a big O that's an exponential, that's really, really awful.
Because it requires way more computing.
Yeah, it requires way more computing power, which means more processor power, more RAM, more everything. Right, Xavier?
So if I'm understanding the operations question right, that just means like every step we're doing, so like the finding how big this rectangles are is an operation,
Yep.
doing the extended rule of them is an operation, multiplying it out for how many rectangles we have is an operation.
Yep.
Okay.
So like for each individual like thing here, right, each individual rectangle, there's like one operation to get the midpoint, one operation to actually plug it in and evaluate it, and then one final operation to add them all up. So it's only like 3 operations per rectangle, which is not bad. There are other variations of midpoint rule. One of those variations is left endpoint rule. So instead of taking the midpoint of the subinterval, you take the left point of the subinterval. And then the other one's right endpoint. As a theme going forward, something that is true about left and right endpoint rules is they're just not as good as midpoint rule from any perspective. Midpoint rule converges faster, and it does have the same number of operations as those other ones, so midpoint rule is just better. One of those weird things. The second method here, method 2, at least method 2 of what all share. There are lots of different ways of getting various kinds of numerical approximations. This is called trapezoid rule. Instead of these ugly rectangles and their like little sharp corners up here, wouldn't it be great if we just stuck in a trapezoid inside? Right, that looks way better, right?
I don't remember that.
That don't look like no trapezoid.
Trapezoid is a rectangle without the angles.
Yeah. It's just not like one of those pleasing,
I don't remember the area of trapezoid.
This don't look like no damn trapezoid.
You don't remember the area of trapezoid? Well, good news. It's the area of a rectangle plus a triangle.
But the triangles have, oh wait, no, their angles are fine. So that's what, some more.
No, it's
Oh, it's
worse. What?
Is it one more?
No, it's worse.
Oh, it's worse.
It's worse.
The angle of each one.
Thanks for the gift, man.
Yeah, because we need to figure out this height right here, because area of a triangle is base times height. Also means we need to figure out this height, which means I need to figure out stuff about that diagonal line,
Yeah.
which means I need to figure out that diagonal line.
So it's kind of like combining left and right points.
So you have side, side. Oh, you don't have the third side.
Remember I said it gets worse? For this one singular trapezoid, you got 2 points. You get to go find slope by doing y2 minus y1 over x2 minus x1. And then you get to go plug that into point slope form too, which means now you got substitution steps in here now as well.
Oh, that's a trapezoid.
And you need to do this and hold this line information in your head or in your RAM for every single trapezoid for the entire thing.
Do you have to hold the whole line information, or can you just start it once you find the full trapezoid?
Because you need to keep the information stored in your RAM somehow. Yeah, what?
Can't you just average the bases and multiply by the, like,
Average the bases.
or I mean, like, yeah, the bases of trapezoid. So like, if that first trapezoid was, the left line is 4 and the right line is 3, average that, that's 3.5 times the width, which let's say is 2,
Maybe.
so.
I'm gonna say maybe on that. And the reason why I'm saying maybe and dodging your question is when we get down to these 2 questions here. So hold off on trying to make this better than what it is until you see these. Similar kind of thing when it comes to talking about rates of convergence and number of operations here, right? Where the number of operations here does seem like it's going to be, at the very least, bigger than midpoint. Like, can we at least agree there? Number of operations, at the very least, it's bigger than midpoint rule. The real sort of proverbial slap in the face is the rate of convergence.
And that's why you need the line information.
You need the line information just to get your approximation. Right? It's part of just actually evaluating what everything is. The rate of convergence is how quickly does your answer for this method go to the actual answer.
And you said rate of convergence is just doing that same method but on a circle and trying to get towards 5?
That's usually how we measure like rates of convergence for like practical purposes for different algorithms. Is if we have a brand new algorithm and we want to know how good it is, we set that algorithm's purpose to calculate pi. And then we can compare it with like known approximate values of pi because we know pi's like a couple billion digits at this point. Rate of convergence here. Is on the order of a cubic. Oh man. Which means as far as the rate of convergence goes, there is 0.2 trapezoid rule. That's why I kind of cut you off there, Blake, sorry. Trapezoid rule, it's neat, it looks cool. I've certainly made a few GIFs demonstrating trapezoid rules, but they don't converge fast enough and they're not worth the number of operations. This is where I'm gonna draw like a little crown on midpoint rule. Because as far as the rate of convergence goes and as far as the number of operations is concerned, midpoint rule is still the winner. In fact, if I remember right, even if like we actually like took a look at the formula for the rate of convergence, I think midpoint rule is twice as good as trapezoid rule. I think it's the length of the interval cubed divided by, here I think it's divided by 12k cubed, and that's where we're getting the cubic. And over there I think it's 24k cubed. So I think this one's just worse, if I remember right. Trapezoid rule is bad. Don't use trapezoid rule. It's awful. It just looks really nice. And because it looks so nice, this is where, you know, early theoretical computer scientists and math people went, it looks so good. Why doesn't it work out better? And it's just bad.
The areas aren't like different between midpoint rule and trapezoid rule?
As far as the rate of convergence is concerned, no, they're not that different. This next method is genuinely better from a rate of convergence perspective. I believe this is on the order of, what's 5 quintic? It's degree 5. A here, B here, what's another A? And so I've been using blue for my little approximations here. We're only going to do 2 subintervals here. And this is a truly and genuinely different kind of algorithm for trying to approximate these particular things. Right? In the past, we fit various geometric shapes underneath the curve and then found those areas in the map. This one is going to feel better because there's going to be an actual integral that we're going to evaluate. And because of that, at least that's my theory as to like why the rate of convergence is better here. But you'll see from the algebra perspective why the number of operations might make this an undesirable algorithm. Oops, I missed.
best fit are integratable.
Hmm?
Those lines of best fit you have derivatives.
Yep, there's 3 points there. And if you're looking to interpolate a function or relationship when you're given 3 points exactly, you're making a quadratic. These are parabolas. So the idea here is to take the left, mid, and right points of the subinterval and not extrapolate but interpolate a quadratic. So this is something that may or may not come up in the study of quadratics and polynomials in algebra classes. To get a line, a straight line, a degree 1 polynomial, you need 2 points. Right, you need 2 points for the slope calculation. To get a quadratic, you need 3 points, right? And this is usually demonstrated by the 2 x-intercepts and the y-intercepts. Right, 2 x-intercepts tells you where it's at, y-intercept tells you whether it opens up or not. And then for degree 4, degree 3, you need 4 points. For degree 5, you need 6 points. You need 1 more than the degree to interpolate an exact function. You got 3 points here, we get a degree 2, we get a quadratic. So we have, and I'm going to use subscripts here, XL, YL for the left point, XM, YM, midpoint, and XR, YR for the right point. Left, mid, right. Okay, good. Yeah, okay. And then now we get to interpolate a quadratic for this particular thing. And this is how we're going to get that quadratic. So fit and ax squared plus bx plus c is equal to y for this particular data. And we got 3 known points, so we're going to plug them in. For the purposes of, I suppose, demonstration, I'm going to pick a couple of points here. And I'm going to make it nice and easy to plug in. Yes, this should be a downwards going parabola. So let's imagine this being my left, this being my right, and this being, no, I want this to be my right, and this to be my right. So we're going to plug each of them in. We got a -1 squared plus b -1 plus c is equal to 2. Then we get a 0 squared plus b 0 plus c equals 4. And then a times 1 squared plus b times 1 plus c equals 2 again. This should look pretty familiar. It's a matrix, it's a linear system. And we know how to solve linear systems. we even know how to solve them exactly. We plug them in as matrix, we get REF, we pick the coefficients, we call it there. Right, Blake? Can be solved exactly. What was that say?
I said the algebra wouldn't be that bad either.
For this particular
Yeah.
example, right? But consider for a second that these numbers are probably not going to be quite so nice. Also, consider the fact that you're doing this linear system solving for each sub.
I'm not even in the back.
More so than ours, we have some more.
I'm at the
And
front.
Solomon, this is where I'm gonna ask you, our resident expert on big O notation. Solving linear systems as far as number of operations are concerned, is that good or is that bad?
Really bad.
It's kind of really bad. Yeah, we can solve linear systems. We got some pretty good algorithms for solving linear systems. But the fact that this makes a square and a square is an area means our number of operations is actually kind of limited to how low it can go. Solving linear systems is kind of computationally complex. Yeah, Xavier?
For this method, can we get complex numbers now or?
Nope, still no.
Still no.
Still no.
Still no.
No complex numbers.
Okay.
So you're solving a linear system numerically, which is bad on its own, for each subinterval, which is going to determine our accuracy, which is also bad on its own because, you know, how many subintervals do you really want here, right? And at the end, you're going to end up with something that you can integrate exactly, but then you got to go through inverse power rule and plug in numbers for fundamental theorem of calculus. This is all trying to describe the fact that the number of operations here is quite big. Right, Solomon?
Yeah.
There's just a lot going on per step. So, number of operations. I'm gonna talk like my good old Brazilian friend Magic. And I'm gonna say the situation is insane. But the rate of convergence is degree 5 is quoted.
So you'll get
Wait, what does
closer with a smaller amount of
quintic?
iterations with per element of the input rule, but that those number of iterations take up more time than the input rule.
More time, more operations, more RAM, more processing power. And this is where sort of the art of computer science and computer engineering comes from, Solomon. How do you know if this is worth it? I don't know the answer to that question. I'm not a computer engineer. How do I know it's worth it? I don't do that. So that's how I know. I just use midpoint rule. It's super easy to program, and it converges on the order of a qubit. Is usually all the accuracy we really honestly need for most cases. So I'm going to make midpoint rules crown even bigger. Make it a fancy crown. It's nice and easy to program. Its number of operations is small. Converges on the order of a cubic. It's better than trapezoid rule. Let's not be fair here. That's not a tall task to break. This particular algorithm is called Simpson's rule. You'd be surprised how much math is in The Simpsons, but no, this is not the same Simpsons.
I would not be surprised.
Oh, it's not, it's the Simpsons.
And from the computer science point of view, whether or not to use Simpson's rule or whether or not to just use midpoint rule, I suppose depends on the kind of accuracy and kind of situation you're in. I don't actually know for sure. I'm not a computer engineer. All I know is that for my purposes, I usually found Simpson's rule kind of cool to think about, kind of cool to draw. The fact that it works out, the fact that this can be exact and solved every single time is cool from the linear algebra perspective. But once it comes down to actually using it, the number of operations is kind of nuts. And it might not be worth it in some cases for that increasing rate of convergence, even if it is by 2 degrees. So I think I said earlier near the start of this is going to be kind of a disappointing conclusion. And you might all be aware of what that disappointing conclusion is, right, Brandon? You should just use midpoint rule. It's sad, but it's just what it is. These are the 3 methods for numerical approximations for integrals that Stewart covers, and these are the 3 that I'm kind of aware of. I don't really know of any other, at least for integrals, that we do come up with. Most everyone in here has to take diff EQ, right?
Is that Calc 3?
That's Calc 4.
Oh,
I think so.
I hope not.
If you're going into engineering, you're going to have to take diff EQ and linear algebra. And in that, you'll be solving differential equations, and one of the topics that you'll be talking about is numerically solving differential equations, of which there are more variations and more important and like useful variations than just intervals. Yeah, Xavier.
I realize this is kind of off topic, but can you work backwards from area under a curve to get curve?
Yeah,
Yeah.
it's called the derivative.
Right, my bad.
I had to think about that for a second and be like, how do I interpret this? Oh, that's what he means. Okay, yeah. Inverse operation of integration is derivative.
Yeah.
It's a good question to ask. Like, there's a lot of things being thrown around to just make sure we know where we're at. So it's a good question to ask. Okay. Guess what's not going to be on midterm and or finals? Any and all of this stuff. Although I might give
Period.
you a midpoint rule question in August, like the practice sheet problem from forever ago.
Did we do something earlier?
Yeah, like there's like a pool and
Yeah.
we're given like various different measurements. You might be given something like
The
that.
plane wing.
Yeah, the plane wing.
Yeah.
But like I won't be like, here's a random function that I made up that doesn't have a closed form antiderivative. Use midpoint rule to get this amount of accuracy. No, you'll just be given like another pool with different numbers in it or something like that.
That's still on Wednesday?
I thought it was on Friday, wasn't
Oh, next Friday?
it? Right?
You said the 15th.
15th? That's for my trig class. They
Oh.
don't have a Friday class. They're just Monday and Wednesday. Right, so they get their midterm on Wednesday, on the 15th.
Okay.
Ours is the 17th.
Yeah, whatever that Friday is. I assume the 17th, but I don't know how to count.
7 days.
Yeah.
Yeah, but
Yeah. Part of the Simpsons. All right. Which I believe makes it time for our usual Friday entertainment.